Differential and integral operations 4. Use the subscript summation notation to verify the following identities. Part A. Divergence of a scalar function f multiplied by a vector a is f times divergence of a plus a dot product with gradient of f. And part B. Curl of a is gradient of the divergence of a minus Laplacian operator applied to vector A. So these are the two we will work on in this video. So let's start with the divergence of the product of the scalar function f with vector A. Now we have our del operator written in subscript summation notation, del xi ei hat. This is to be, we have to perform a dot product with f times vector a, which is aj ej hat, and this dot product will involve the dot product between two unit vectors ei hat and ej hat, and then we have the del operator del xi acting on f times jth component of vector A. Now we know that the dot product between ei hat and ej hat is Kronecker delta ij, and then we have del xi f times aj. Now the Kronecker delta is only equal to 1 when I is equal to j, otherwise it's 0. So we will set I is equal to j. So del xi is what we had, and then we have f, instead of aj, we have fai. Now we're performing differentiation on a product of two quantities f and ai. This is equal to ai times the partial derivative of f with respect to x plus xi plus f times the partial derivative of ai with respect to xi. So that's what we have here. And here I recognize this is multiplied by 1, so I can say that this is ai ei hat dot product with del f del xi ei hat, because ei hat dot ei hat is equal to 1. So del f del xi ei hat, that's basically a vector dot product with the gradient of f. And on the other hand, here I have plus f times del xi ei hat dot product with ai ei hat. That's just the divergence of a. So this is basically giving me the final answer for the divergence of the product of a scalar function f with a vector a. This is equal to vector a dot product with gradient of f, and the second term is f times the divergence of a, the vector a, or the vector field a. All right. So that's the end result of the calculation. Let's check. It was supposed to be this, so it is correct. Now for curl of a, the part B, we can write the cross product as epsilon ijk, Levi-Civita symbol, ei hat, del xj, the jth component of the gradient operator, and kth component of curl of A. All right, and this is equal to epsilon ijk ei hat del xj. Now we're going to write curl of A's kth component, that is epsilon klm, and del xl applied to am. Normally there would be an ek hat here, but it's the kth component, so we have just the component itself. Okay, now we can put these two Levi-Civita symbols together, epsilon ijk, epsilon klm, and then operate this del xj on del xl of am. So let's do that. This is equal to epsilon ijk epsilon klm ei hat del xj applied to del am del xl. Now we can change the order from klm to lmk. So remember that we have this cycle where if we're going from K to L to M, this is all going to be plus 1. So KLM, so we have this order here. KLM is plus 1, also LMK is plus 1. So we can go from IJK, KLM to IJK, LMK. So we can rewrite this as epsilon IJK, epsilon LMK, reordering the indices, ei hat del xj del am del xl. Okay, and now we can use the Levi-Civita identity because these two indices, the common index is in the same position. Kronecker delta, first indices IL, firsts IL, then seconds JM, minors inners JL, and outers IM. So firsts, seconds minus inners, outers. This is multiplied with ei hat del xj del am del xl, and now Kronecker delta IL tells us that L is going to be equal to I, so we're going to keep the I, ei hat, and J will be equal to M, so it will be del xm, and then we have del am del xi, because L is to be equal to I. And then we have the second term, which says J will be equal to L and I will be equal to M. So we're going to keep the I here, ei hat. So J will be equal to L del xl, and I will be equal to M, so del ai, M will be equal to I, del ai del xl. All right. And this is equal to EI hat. Now you can see that the order of the derivatives doesn't matter, so I can reorder it as del xi, del am, del xm, which is the gradient of the divergence, minus, then I can do a second product, second derivative, del squared del xl squared, applied to vector ai ei hat, and that is equal to gradient ei hat del xi of del am del xm, that's the divergence of A, minus the Laplacian del square applied to vector A. So my final answer is curl of A is equal to gradient of divergence of A minus Laplacian A. So that's the final answer. Let's check this final answer. Gradient of the divergence of A minus Laplacian applied to A. So we use subscript summation notation to verify these two identities. Divergence of a scalar field multiplied by a vector field A is A dot product with gradient of F plus F multiplied with divergence of A. And first we write the del operator as del xi ei hat, and a vector A is aj ej hat. The dot product between ei hat ej hat gives us Kronecker delta, which sets I and j equal, so this j becomes equal to I, and Kronecker delta is equal to 1. And now I apply the differentiation to a product of two functions. The first function multiplied by the derivative plus the second function multiplied by the derivative of the first. And this gives me basically ai ei hat dot product with del f del xi ei hat. So I recognize that this is gradient of the function f. This is the vector a dot product. And here I have f multiplied with del xi ei hat dot product with ai ei hat, and that's basically the del operator dot product with a vector, which is the divergence of A. As for the second identity, for the curl of a vector, we have epsilon ijk ei hat del xj kth component of the second vector. And kth component of curl of A is epsilon klm del xl applied to am. If this wasn't kth component, this would be E multiplied by ek hat. Okay. And epsilon ijk epsilon klm can be written as epsilon ijk epsilon lmk. And I didn't touch the rest of the expression. And for this one, I used the cyclic permutations klm is equal to epsilon klm is equal to epsilon lmk is equal to epsilon mkl, etc. And Kronecker delta firsts il, Kronecker delta seconds jm, minus Kronecker delta inners jl, outers im, multiplied by this. Now L will be set equal to I, so this will be ei hat del xi, and j will be set equal to m, so this will be xm del xm del am. And as for the second term, j will be equal to L, so this j will become L here, and I will be equal to m, so m has been replaced by I. So I see that I have second derivative of the ith component of vector A in ei hat direction, and here I have ei hat I can change the order of these derivatives, del xi, del am, del xm. So del am, del xm is the divergence of vector A. Ei hat del xi is gradient, so it's gradient of the divergence minus Laplacian second operator, second derivative applied to vector field A.